Hello friends. So today we are going to solve a question which was asked in 1995, and in this question a metal rod OA, mass m and length r, kept rotating with a constant angular speed omega in a vertical plane about a horizontal axis at the end O. The free end A is arranged to slide without friction along a fixed conducting circular ring in the same plane as that of rotation. A uniform and constant magnetic induction B is applied perpendicular and into the plane of rotation as shown in the figure. An inductor L and an external resistance R are connected through a switch S between point O and point C on the ring to form a electrical circuit. Neglect the resistance of the ring and the rod. Initially, the switch is open. So based on this, we have total 3 questions. Total, we can say 2 parts, and B part is having 2 subparts. In part A, it is asked what is the induced EMF across the terminal of the switch. In part B, the switch S is closed at time t is equal to 0, and based on this information we have 2 sub questions. In the first part, obtain the expression of the current as a function of time, and second, in the steady state, obtain the time dependence of the torque required to maintain the constant angular speed, given that rod OA was along the positive x-axis at t is equal to 0. So we have the given figure, and in this figure it is given represented as magnetic field B, which is into the paper, and we have a rod OA which is along the x-axis initially at t equal to 0. So initially at t equal to 0 we have OA along x-axis, and it is rotating in this direction, and we have to find out first of all what will the induced EMF across the switch S, and initially this switch is open. So let us solve part A. We know the induced EMF E is equal to minus d phi upon dt, where phi is the magnetic flux. So we can also say that our magnetic flux phi is equal to magnetic field multiplied by area. Now it is given that the rod rotates with the angular speed omega. So we are given that rod rotates with the angular speed omega, and we can assume that at any you can say any point at a distance x from the O, its velocity is suppose v. Okay. So you can say that at any point at a distance x, the linear velocity, you can say at a distance x, the velocity v can be written as omega times x. And if we assume that now this rod moves by the distance of dx, therefore, or we can say considering considering a small element dx. So therefore the motional EMF, therefore motional EMF in the small element dx, in the small element dx, we can say its small EMF dE will be equal to B multiplied by velocity and multiplied by dx. And we substitute value of V, which is our omega x. So we can write B multiplied by omega x and multiplied by dx. So now finding through the entire rod, we integrate, and the length of the rod is given as R. Okay. So therefore we can say that the induced EMF, the motional EMF rather, we can say the motional EMF for the entire rod we can write this as E will be equal to B omega integration 0 to R x dx. Now it is a simple integration. This will be B, we have x square by 2, and this comes as 0 to R. So we get the EMF is equal to half B omega R square. So this is our part A. Now we can solve for part B. And part B, it is said that the switch is closed. The switch S is closed. And in the first subpart, we are supposed to find out current as a function of time. Current as a function of time. So now we know the induced EMF in the rod, which is rotating. So we can draw a approximate circuit replacing the rod by this EMF E. And we get this as, this is a switch which is now closed, and we have resistance R, and along with that we have a inductor L, and we can say this is our EMF induced. Sorry, this is the inductor. So here we can use the Kirchhoff's law. Using the Kirchhoff's voltage law, and the induced EMF will be equal to L di upon dt plus IR. And induced EMF we already know, we found out in part A. We can write this as half B omega R square is equal to L di dt plus IR. Now this is our first order differential equation. This is first order differential equation. Therefore its solution will be, we are going to get I of t is equal to I max, and it comes as 1 minus e raised to power minus r upon L multiplied by t. And I max is steady state current. We can find out its value. We know that our I max is our steady state current, which will be equal to induced EMF divided by R. So we can write this as half B omega R square divided by resistance R. Therefore, we get the current as a function of time. This becomes B omega R square divided by 2R, and 1 minus E, this comes R upon L multiplied by T. So this is the first part of, you can say, the equation. This is for the first part of B. Now we come to the second part. The second part, we are supposed to find out the torque. So first of all, we are going to find out what will be the force acting on the rod due to the induced current I. The force acting on rod due to induced current I, and that force is our F, which is equal to B multiplied by current I and length of the rod, which is our R. We substitute value of I and we get this as B square, and we have the R cube omega divided by 2R 1 minus E minus R upon L and multiply by T. Now this, you can say, force will be generating a torque about the middle of the rod. From here we can say that this force will produce the torque, and the torque represented as tau will be equal to F multiplied by R upon 2, and this gives us B square R cube omega divided by 4R 1 minus E minus R upon L multiplied by T. And this torque will be acting, if you want to find a direction, we can also say that this torque will be acting in clockwise direction. This torque will act in clockwise direction, and I think this was the only thing that is asked. In the steady state, obtain time dependence to maintain the constant angular speed. Yeah. So in order to maintain the constant angular speed, external torque needed to be applied in anti-clockwise direction. Okay. So you can say that because this torque will be because of the force that is acting on the rod due to induced current. Okay. So in order to balance that, so that the rod rotate with the angular speed of omega, we need to apply external force whose magnitude will be equal to the torque that is being produced by the induced current. You can say to obtain a constant angular speed omega and external torque needed to be applied in the anti-clockwise direction. With time dependence. So this question was asked in the year 1995, and this completes the question. Thank you.